All right, so here we go, taking a look at lesson 6, which is comparing linear and exponential functions. So this is kind of the stuff that we were doing, or this is the stuff that we were doing right before schools were kind of closed here. So some of it should be a little bit more familiar than maybe some of the other lessons that we've done. So the first two things we're going to look at are the general forms of functions. So the general form of a linear function is f of x equals ax plus b, right? And that should look very similar to when we talked about the slope-intercept formula line, which was y equals mx plus b, right? Here we're just changing f of x for y to represent the function, and then a is our slope, which we represent with m in the slope-intercept formula, but in this case to represent it with a. So it says where a is the slope of the line and b is the y-intercept. The slope of a linear function represents a constant rate of change. So a constant rate of change where we are adding or subtracting, right? So we're counting by either adding or subtracting. For every pair of inputs that are the same distance apart, their corresponding outputs are also the same distance apart. For example, the table below shows the data from a linear function because the difference between each pair of outputs is the same from one pair of inputs to the next. So if we're counting in our inputs, we're counting by 1. So we go from 2 to 3 to 4 to 5. That is the same, we're counting by the same number each time in the input. So then our output should also increase by a constant number. So from 0 to 3, we add 3. To get to the next one, add 3 to get to 6, add 3 to get to 9, add 3 to get to 12. So we're constantly either adding the same positive, or we could add a negative number if these outputs were going down. Now, the other type of function we're going to take a look at is exponential functions. So the general form of an exponential function is f of x equals a to multiplied by b to the x, where a is the initial value or the y-intercept. So one way we put it is a is where we start, and then b is the base, and the base of an exponential function represents a constant quotient of change. So we have b, which is like the rate of increase here. At what rate does this function increase? So for example, the table below shows data from an exponential function because the quotient of the outputs is the same from one pair of inputs to the next. So again, if you look at the inputs and we see that we're counting by 1. So we go from 1 to 2, 2 to 3, 3 to 4. So we're counting by the same number each time. That means that the quotient should also remain constant between the outputs. So if we take the second output, 1.5, divided by 0.5, we get 3. If we take the third output, 4.5, divided by 1.5, we also get 3. So this division, these quotients will all be 3. So this function here, we could actually write, well, actually, we don't have the initial place where it starts because we only have when x is equal to 1. But we do know that the b of this exponential function, right, or the rate of increase would be 3. All right, going down to the first sample question here, it says the function f of x is modeled in this input-output table. So first thing we have to notice here is the inputs. Do the inputs go by a constant amount? So here we're going from 0 to 2. So from here, we're counting by 2. So let's see if that continues. From 2, we add 2, we get to 4. And 6, 8, 10. So we are counting by a constant amount on the top. Then we want to look at our outputs. Are outputs increasing by the same amount or decreasing by the same amount? Or are they different amounts and we have to see if they're the same rate? Well, from 10 to 20, right, we add 10. From 20 to 30, we add 10. 30 to 40, add 10. And we continue to add 10 for each of these from 50 to 60 as well. So whenever we're adding or subtracting, which is the same as adding a negative number, it is going to be linear. So we're looking for a linear function. And when we're talking about linear, we have a common difference. So right away, we can get rid of b and d because this is a linear function, right? So then we have to say, is it a linear function because the quotient of consecutive outputs is the same? Or is it linear because the difference between consecutive outputs is the same? Whenever we have linear, we're looking at the common difference. So it is choice C, and we can eliminate choice A there. All right, going on to the next page here, let's take a look. It says linear versus exponential situations. So certain situations are best modeled using linear functions, while others are best modeled using exponential functions. Typical linear functions model situations that involve unit rates or a constant rate of change, while typical exponential functions model situations that involve growth or decay by the same rate from one input to the next. In the formula that models exponential decay, f of x equals a b to the x, the base is less than 1. So when we're looking at decay, right, our b is going to be between 0 and 1. In the formula that models growth, f of x equals a b to the x, the base is greater than 1. So we're looking for, 2, 3, 1.5. That would show growth. So explain whether each situation is best modeled using a linear function or an exponential model. So the first one here says the amount of water in the lake is decreased by 4% each year. So when we see a percentage, something changes by a certain percent each year, we're looking at exponential. Right? And if you look at their explanation, it says the situation in part A deals with the change that is constant rate from one year to the next. So the quotient of each output will be the same from one year to the next. So an exponential function is the best model for this situation. If we look at B, B says the cost of tuition increases by $25 each year. So this is a constant increase, right? A constant difference. So this one would best be modeled by a linear function. Here it says in part B, the situation deals with a change that is constant amount from one year to the next. The difference between each pair of outputs will be the same, so a linear function is the best model for this situation. Then it goes on to say, some linear functions may look like they increase at a greater rate than some exponential functions since their outputs appear greater than the outputs of the exponential function. However, very important here, however, for any increasing exponential function, the outputs will eventually exceed any linear function. And that is because in exponential functions, outputs are multiplied, not added by a factor, and multiplication increases outputs by a greater amount compared to adding. So if we are comparing an exponential function and a linear function, if the exponential function has a b that is greater than 1, then it is going to eventually exceed any linear function because multiplication increases outputs greater than compared to adding. All right, taking a look at sample question number 3. It says, Amber made the table below showing the outputs of the function f of x equals 2.5x and g of x equals 1.5x. Based on the table, Amber thinks that all values of x greater than or equal to 1, f of x will always be greater than g of x. Is Amber's thinking correct? Well, first she's saying that f of x will be greater than g of x. So f of x here, if we look at the equation, it is a linear, while g of x is an exponential. And then we just read on the last page that if the base, right, is increasing, right, so if we have an increasing base here, which means that it's greater than 1, then it will always eventually be greater than a linear function. So if we take a look, this linear function each time is increasing by 2.5, increases by 2.5, and it'll continue to increase by 2.5 the whole way. If we look at our exponential function, from 1 to 2, it increases by 0.75. Then from 2 to 3, it's going to increase by 1.125. And then if we keep going, it starts to increase by 1.6875. So if we see it's increasing by more and more each time we go down, or each time we go further into the positive numbers with our x's, so eventually g of x is going to be greater. So she is not correct. She is not correct. So we can get rid of our yeses. And then she's not correct, not because of the amount of decimal places, but because exponential functions always exceed linear functions as long as the exponential function has a base greater than 1 And in this case, the base was 1.5, so it definitely exceeded. All right, so now let's take a look. It's your turn. It says, read each problem, circle the letter of the best answer. So which situation is best modeled using a linear function? So linear function, common difference. All right, we're adding or subtracting the same number. The pipe leaks a total of 5 gallons each week. So each week we add 5 gallons more. This is looking like it's going to be our answer, but let's check the other ones here. The value of a coin collection increases by 5%. So whenever we see a percent increase, right, we're thinking exponential. The population increases by 1.5%, again, exponential. And the temperatures is 1.5 times greater than the previous hour's temperature. That is also going to be exponential there because we have a constant quotient. It'd be 1.5 times if we were to divide our outputs. So our choice is choice A, which is just adding 5 gallons each week. Question 2 says, the graph of an exponential function is shown below. Which pair of equations can be used to show that f of x grows by a constant factor over equal intervals? Well, first, we want to take a look. The constant factor over equal intervals means that we are looking at exponential function, and exponential functions, we're looking for the common ratio, right? Which means that we have to divide, and we're looking for like the quotient, right? The answer to the division problem. So right away we can cancel one, A and B, because they're not dividing anything. That's how we would maybe use if we're trying to find a linear function there. So then we look at C and D, and we want their quotient to be equal. So if we look at C, they both equal 2. And D, 1 equals 4, 1 equals 8. So D is not correct, and C is our answer because they have a common ratio there. Now, where did they get these numbers? Well, what we can do is create a quick table here that shows this function here. So we have f or x, and then we have f of x, right, which is also our y values here. So if we do x, we'll just write it for 0, 1, 2, 3, and 4. And now if we want to put in our different y values, so when x is equal to 0, the y value here is about 1/2 or 0.5. When x is 1, our y value is 1. When x is 2, our y value is 2. When it's 3, we go up, our y value is 4. And when x is 4, we go up, our y value is 8. So if we were to find our common ratio here to show that it grows by a constant factor, we take one of the outputs and divide it by the one above it. So if we take 1 divided by 0.5, we'll get 2. And that's what they did here for the first part. Then if we take another set here, 8, and divide it by the output in front, 4, we also get 2. And that's what they did for that second part. Now we could also have taken 4 divided by 2, where we get 2, or this one here, 2 divided by 1, and we would have also got 2. So notice how our common ratio is always 2, right? So that shows that it grows by a constant factor. Choice C. All right, the next one here says, for the function f of x equals 4x plus 5, which statement must be true? So first we're looking at a linear function, so it has a common difference. So it means that it goes up, goes up or down by the same amount each time as we go on our inputs by 1, it will change by a constant rate in our outputs. So here, if we're looking for each output, the first one says each output is 4 more than the preceding output. The second one says each output is 5 more than the preceding output. C says each output is 4 times as great as the preceding output. And D says each output is 5 times as great as the preceding output. So if it's linear, we're not looking at anything that has to do with times, because that's going to be dealing with our exponential functions. And then when we want to know how much it's going to increase, the output is always going to increase by whatever our slope is for our line here. So if we look here, the slope is the number in front of the x, which is 4. So that means that each output will increase by 4. So each time we go, over 1 on the input will increase by 4 on the output. All right, taking a look at questions 4. So questions 4 and 5, which are the last two in this lesson here. Question 4 says, the function f of x is represented in the table. The function g of x is represented in the graph. Which function will have a greater output as x increases, f of x or g of x? So first, if we take a look, g of x here, we can see very clearly is a linear function. As it goes from 0 to 1, it increases by 2, right? So our common difference, right, or our slope here is we're increasing by 2. Now, if we look at our f of x, we can see that this doesn't look like it's increasing by the same amount. So from 0 to 1, it increases by 0.2. From 1 to 2, it actually increases by 0.24. So you can see that that number is getting bigger. From 2 to 3, you can see that it increases by 0.288. So you can see here that this is not a common difference. So this is going to be an exponential function. It's an exponential function. And then if we were to find the rate that is increasing, right, we can subtract our common differences here and find the common ratio by taking one of our outputs and dividing by the previous one. So 1.2, right, divided by 1 is going to give us 1.2. So that means that each time we're increasing by multiplying by 1.2 here. So if our b is equal to 1.2, it means that it's greater than 1. So this is a function that is growing, exponential function that is growing. And we know that an exponential function that is growing will always outpace, it will always eventually get bigger than a linear function that grows at a constant rate. So which function will have greater outputs? F of x, because it is an exponential function that is growing. All right, and that was the key that they said at the very end of the lesson portion of this text, that exponential functions that are growing will always eventually outpace or output. The outputs will be higher than any linear function. All right, explain whether each situation is best modeled using a linear function or an exponential function. So remember, linear means we're either adding or subtracting. And then exponential is when something is multiplying, to increase from one output to the next. So if the price of a clearance item decreases by $10 each week, if it's decreasing by $10, that's a constant amount that we are subtracting. So this would be best to use a linear function to model, because it's a constant amount each week that we're subtracting. The price of a clearance item decreases by 10% each week. So once we change this from $10 to 10%, now we're actually going to be using an exponential function. And this will be an exponential decay function because it is decreasing. And we're decreasing by 10%. So the actual amount is going to change that we decrease each week, but that rate will always be 10%, and that's why we would use an exponential function. All right, so this is the end of lesson 6. So go through, make sure you get all your answers down, and if you have questions, make sure to reach out.